Hello everybody, welcome to the video for topic number 6, an introduction to functions. In this video, our objectives today are to define what a relation is, what the domain and range of a function are, how to identify whether things are functions or not algebraically and by using the vertical line test graphically, to find the domain and range of functions, and show you how to use function notation. Let's start with some definitions. First, we have a relation. A relation is a set of ordered pairs where the first component corresponds to the second component in a matter where the first component is x and the second component is y. So essentially anything that you can put as a coordinate is a relation. The x value is referred to the input of the relation and the y value serves as the output. Now we have some other names for the inputs, the outputs, so we don't have to keep calling them input and output. We're going to refer to the input as the domain, so the set of all the first components. So again, the way you can think about it is all of the x values are what we're considering the domain, and the y values, or what we're calling the outputs, are called the range. So a lot of the times you're going to hear me commonly refer to the x values as the domain and the y value as a range. And in a function, the domain is what you input into the function, and you output the range. So again, in this example, find the domain of the function s, which is these three coordinates. Simply put, we would call the domain 1, 3, and 5, because those are all the x values. And then we would call the range 2, 4, and 6, because those are all the y values. If they want you to create a mapping technique, all we're going to do is we'll put the domain over here, and we'll list all the values of the domain, and the range over here, and we'll list all the values of the range, and we'll put which parts of the domain correspond to which parts of the range. So in this case, 1 goes with 2, 3 goes with 4, and 5 goes with 6. One thing to keep in mind here, not all relations are functions. We're going to learn that in a second, but not all relations are functions, but all functions typically are derived of relations. A function is a relation where each element of the domain x corresponds to exactly one element of the range y. So to summarize it, each x has one unique y value. If it has more than one y value, it is not a function. So we're going to take a look at each of these examples, and we're going to see, do they represent a function? So in the first example A, we have gas station and price. We're going to call the gas station our domain and the price our range. And our question here is, does each of the gas stations have exactly one value in the range? Meaning, does each gas station only have one price? We look at Valero, and it only has one price of $3.19. We look at Shell, and it only has one price of $3.29. We look at Texaco, and it only has one price of $3.35. And we look at Citgo, and it only has one price of $3.29. So is this a function? Yes. Each value in the domain only has one value in the range. They can share the same value. You'll notice Shell and Citgo both share the same value, but they cannot have multiple values, meaning Valero, as it goes to $3.19 now, can't go to any other price at the same time. That would make it not a function. Let's take a look at relation S. Let's write it as a map. So if we show it as a map, we would take all the values that we have in the domain, -2, 4, and 0, and all the values we have in the range, 3, -1, 2, -5, and we would correspond them. -2 goes to 3, 4 goes to -1, 0 goes to 2, and 4 goes to -5. Now if you notice over here, if you look at 4, 4 is going to both -1 and -5. One x value is going to two different y values. So is this a function? No. That x value cannot go to two different y values. The same x value can only go to the same y value. It cannot go to different ones. Here we have a table. X again is the domain, and y is the range. does each value in the domain go to each value once in the range? And if you'll notice here, our domain is all different, meaning we don't have any values that repeat. This is a good indication that yes, this is going to be a function. There's no value of x that goes to more than one value of y. Let's look at one as a word problem. The set of all U.S. presidents is the domain, and the range is the years in which there was a presidential election. So you have to ask yourself, is there any value of x that goes to more than 1 year of y? And in this case, this would not be a function. An example is currently what we have right now. If you look at President Trump, he has been elected twice, once in 2016 and once in 2024. Trump would be the domain because he is a U.S. president, and it's going to 2 different years in which there were a presidential election. That means this is not a function. So to recap, let's give you some tables that may be tricky and decide if they're going to be functions or not. What if I gave you the x values 1, 2, 3, 4, and all the y values are the same? Let's say they all go to 7. The question is, do each of these x's go to one unique y? Here, 1 only goes to 7, 2 only goes to 7, 3 only goes to 7, and 4 only goes to 7. So yes, this would be a function. The same x values can go to the same y values. Let's look at it the other way. Let's say all the x values were 7s, and the y values were 1, 2, 3, and 4. Well, the first time I have 7, it goes to 1. But then I have 7 again, and it goes to 2. The same x value is going to 2 different y values. No, this would not be a function. In order for it to be a function, the same x value has to go to the same y values. Let's take a look at this one. I've got 1, 2, 3, 4, and 2. And then for my range, I've got 5, 6, 7, 8, and 6. So we've got to check, does every x value go to each y value once? So if you look at this problem, 1 definitely goes to 5, and there's no other 1s. 3 goes to 7, and 4 goes to 8, and there's no other 3s and 7s. But take a look at 2. 2 goes to 6. Then we have 2 again, and it still goes to 6. So if you take a look, does each time we go to 2, it go to the same number? In this case, the answer is yes. So this is still a function. This is okay. The 2's are going to the exact same value. What would make it not a function is if they went to different values. So I'll go back to the same example. Let's say we had this, but this time instead of 2 going to 6, 2 goes to 9. Now it's violating the rules. 2 is going to 2 different numbers. So no, this is not a function. Again, in order for something to be a function, each value of x has to go to each value of y only once. If an x value goes to multiple values of y, it is not a function. If we're given a graph, we can use the vertical line test to be able to go through and prove if something is a function or not. So we'll go through and we'll look at it here with that. Let's do it with these graphs here, and these graphs we'll play around with in Desmos. So if you look at this graph, y equals x squared, we'll be able to go through and see. If a vertical line can pass through more than one point, it is not a function. So if I draw vertical lines anywhere on this graph, you'll notice every time I draw a vertical line, it only hits the graph at one point. There is nowhere on this graph that I can draw a line and it hits it more than once. So yes, this would be a function. Whereas if you take a look at B, if I draw a line through here, it hits it twice. Now, does it hit it once at some points? Yes. Technically, if you do it here at the vertex, it only hits it once. But I have to be able to draw a line, vertical line anywhere through it, and it only hit once. Here I drew a vertical line, and it hit 2 times. So is this a function? No, this is not a function. Let's take a look at this value. Again, I can draw a line anywhere through this, and even though it looks like it's getting close to here, it's always continuously going down, and always it is only hitting the graph one time. So yes, this is a function. You could try and graph these on your own, but as you go through and do it, x squared plus y squared, anytime you see it look like that, it always comes out to be a circle. A circle, when you draw a line through it, will never be a function. So no, this is not a function. The other one I want to point out here is this one. This is what we're going to call a linear graph. It's linear because we have x just by itself. So it's a graph that looks something like this. Anytime we have a graph that looks like this, we could draw the line straight through it. Linear graphs will always be a function. So in this case, yes, this is a function. Try this one on your own for letter E. You should be able to graph it and see if it is a function or not. Domain and range graphically. So again, let's remind you, the domain are the x values, and the range are the y values. When we take a look at graphs, we want to be able to express their domain and range, saying we want to be able to tell all the x and y values that exist within it. Again, to solve these, we're going to put our answer in interval notation. So we have to go back and remember our rules. Open dots are going to end up being parentheses. Closed dots will end up being brackets. And anything with infinity, whether positive or negative, will end up having a parenthesis around it. As we look at graphs, we're going to look at first the domain, which is the x values, and then we'll head to the range, to the y values. So for the domain, we're going to look at only these values across the x-axis. And we're going to always start with the far left side. We're going to ask ourselves, what is the smallest x value that this graph can hold? So if we go to this point here, furthest to the left, we see this is the smallest it can be, and it corresponds with the -5. So we're going to put -5 to our left side, and it's got a closed dot, so it gets a bracket. Now all these values exist, and we're going to go to the biggest value that it can be xy's, which is this point. This point corresponds with 4 on the x-axis. So we'll go -5 to 4. However, this has an open dot, meaning it can't equal 4. So we're going to put a parentheses at 4. So this domain says I can pick any number between -5 and 4, and an x value will exist. I can pick -5, but I cannot pick 4. For the y values, we're going to look at the y-axis and do the same thing. For the range, we're going to start with the smallest the y value can be. So if I go down here, this dot is the lowest it can be, and it corresponds with a y value of -4. So I will put -4 to the left, and because it's a closed dot and it can equal it, I'm going to put a bracket around it. We'll then go up and see the highest that this point can go to, and we notice here is the highest point that it can go to, and it's +4. However, because it's got the open dot, it cannot equal 4, so we will use a parentheses. Now on this problem, we have an arrow, and again our arrow is an indication that we're going to have an infinity. Now remember, this arrow is telling us it's going forever in 2 directions. This arrow tells us it's going down forever, and it's going to the left forever. That's going to be important when we get to interval notation. Again, for the domain, we're looking at the x values. We're looking at left and right. So as I go to the left, I notice I get to the arrow, which means it's going forever to the left. It's going forever to the negative numbers. So my domain will start at -infinity, which always gets the parentheses. For the right side, it does end at a higher number. It ends at 3. It doesn't go forever to the right, so it's going to end at 3. However, it's got an open dot, which means it can't equal 3, so we'll put a parentheses at 3. Now for my range, we're going to look bottom to top. So if I start all the way at the bottom, again I get the arrow, which means it's going down forever. That means the range is -infinity. It's going to continuously go down, so there's no number it's going to stop at for the bottom. For the top, we'll go to the highest. Again, this point represents the highest. That's 16. But we can't include the 16 because it's got an open dot, so it will get a parentheses. So the domain is any value between negative infinity and 3, and the range is any value between negative infinity and 16. Let's do a couple more. In this value, we've got this here, this arrow. This is going up and to the right forever. So again, we'll get to that when it gets to the domain and range. For the x values, we'll go all the way to the left, and we'll see that we have a negative 2. So we're going to include the negative 2 as our smallest point, and it can equal the negative 2, so it gets a parenthesis. And as we go to the right forever, we get a arrow. This value means that it's going to go to the right forever, which means it's going to keep getting bigger. So it has got a positive infinity. Infinities always get the parentheses. Now for the range, we're going to start at the lowest point. Here, this bottom is the lowest point. The lowest point here is this negative 4. And because it's part of the solid line, we'll include it, so it gets a bracket. And again, it's going to go up forever. Up is positive infinity, but on the y-axis. So it's going to go positive infinity to the right. We will not do this problem, as this is the problem we just previously did. So one of the things that we're going to remember here with infinities, if it goes down forever, that is basically negative infinity for the range. If it goes up forever, that is positive infinity on the range. If it goes to the left, that is negative infinity for the domain. And if it goes right forever, that is positive infinity for the domain. You can think of domain as left and right, and range as up and down. If it's got a dot, that means it won't go to infinity, and it'll have a number in its place instead. Let's try it on this graph. Find the domain and range, and express the answer in interval notation. So here, we actually have two sets of arrows. So let's understand what these arrows means. This arrow means it's going down and to the left forever, and this arrow means it's going down and to the right forever. When I look at domain, I'm asking how far I can go to the left and how far I can go to the right. Well, we've already proven it's going to go to the left forever, so that means it's going to start from negative infinity. And we've also proven it's going to go to the right forever with this other arrow, so that means it's going to go to the positive infinity. So basically it's telling you here the domain is any value of x. Now for the range, we're going to look down and then up. We see that both these arrows are going down, which means the range is starting from negative infinity. But when we go up, it'll eventually stop at some point, and it's going to stop right here at this point with a y value of 2. So we'll go all the way up to 2, and because this is a solid line with dots, we can include the 2, so it'll get a bracket. So in this case, the domain is negative infinity to positive infinity, and the range is negative infinity to 2. Function notation. So all throughout our algebra life, we've been given stuff like y equals 3x plus 2. And we say, well, what happens when x is equal to 4? You used to go and you used to plug in that 4 into the equation, and you would solve for y. And then we would get y equals 14. This is no different than that. The only difference is we're putting it in function notation, which means we're going to have to find the function that it goes into and input it into the correct function and get its output back. So for example, for f of negative 2, I see that I have three functions, f of x, g of x, h of x. I need to plug this negative 2 into the f function. So I'm going to take this function here, which is f of x, and all I want to do is be able to find f of 2. If you notice, all I did was take the x and replace it with negative 2. I'm going to do the same in the equation. So negative 2, and instead of x, we're going to put negative 2 here, plus 1. So again, I just took out the x and I replaced it with what I'm solving. Negative 2 times 2 is 4. 4 plus 1 is 5. That tells me that f of negative 2 is equal to 5. This is no different than saying that when I plug in x at negative 2, I get back an x value of y. Let's try it again with the g function. So this time, I need to plug it into g of x. G of x is equal to the square root of 3x minus 5. And I want to solve for g of 3. So all I'm going to do is I'm going to use the exact same function, but where it says x, I'm going to plug in a 3. And then I'm going to go through and evaluate the number. As I do this, 3 times 3 is 9. 9 times 5 is 4. The square root of 4 is equal to 2. So g of 3 is equal to 2. Let's do it one more time. I want h of negative 1, so it's going to have to go into the function for h. Now you notice this time there's multiple x's in my h function, but each one of them are getting replaced with negative 1. And I'm going to put parentheses around it as I do it. So x squared should be negative 1 squared. Negative 2 times negative 1 plus 3. Then we'll go through and use PEMDAS to solve this. Negative 1 squared. That's negative 1 times negative 1, which is positive 1. We'll then do negative 2 times negative 1, which is positive 2, and then plus 3. 1 plus 2 plus 3 equals 6. So we can say h of negative 1 is equal to 6. So this is no different than what we've learned algebraically before. We're just putting it in function notation. We're taking the value that's inside the parenthesis and plugging it into the correct function to be able to solve it. We can also do this with a graph. So here, they want us to find f of 6 and f of negative 21, and they only give us the graph. A reminder that when I look at functions, it's f of x equals y. So I'm taking the x function and I'm trying to find a y. So when I look at f of 6, I'm really asking what happens when x is equal to 6. So I need to find that on the graph. I'll go over the graph and I'll see that here is when x is equal to 6. The y value that comes back is negative 6, so f of 6 is simply equal to negative 6. Same thing with 21. I'm going to go through and I need to find what happens when x is, negative 21. Place that, negative 21. So I need to go through and figure out what is the x value when it is at negative 21. I go to my graph, and here's the x value at negative 21, and the y value it comes back with is negative 6. So f of negative 21 is negative 6. Let's try one more just so we make sure we get the hang of it. What if I wanted f of negative 9? So again, it's actually asking if you're at x at negative 9, what's the y value? So I look here, and I take its y value, f of negative 9 equals 9. Letter B is the opposite. It says find all the values of x such that f of x is equal to 0. So again, as we go through this, remember f of x is the exact same thing as y. So when it says find all the values of x such that f of x is equal to 0, it's saying find all the values of x where y is at 0. So as I go through and I look, there's 3 points where I see y equals 0. We have 1, 2, and 3. All 3 of these points that I'm putting a star next to have a y that's 0. That means their x values are the solutions that I'm looking for. So we would say the x's are negative 18, negative 3, and 12. Those are all the x values that when I plug them, find them in the graph, they come back with f of x equaling 0 or y equaling 0. Finally, let's find the domain and range of x. And we're not going to express it in set builder notation. Let's go ahead and just do it in interval notation. So again, domain, I want the smallest value of x and the largest value of x. The first thing I'll notice is there's no arrows here, so there should be no infinities. The smallest value of x we see is this x at negative 21. So we will put negative 21 as the smallest value, and it's got a closed dot, so it gets a bracket. The largest value of x that exists is 18. So my domain is negative 21 to 18. Both have brackets because they both have closed dots. Y value lies. The smallest y value I see is negative 6. It will also get a bracket. And the highest y value we see is this 9. So our range will go from negative 6 to 9. So again, final reminder that domain is really just the x values and the range is the y values when we go through and do this.